as Demetrius said, my name is Carl Steinbach. Quick correction, I actually left LinkedIn at the beginning of March, and I'm working on something new now, which hopefully I'll be able to share with everyone in a couple of weeks. But I'm here today to talk about work that I did at LinkedIn and work that still very much influences the way that I view the data ecosystem and the future really of this platform. So the title of the talk is Exploiting the Data Code Duality with Dali, and Dali is the name of the project. I wanted to start by talking about a paper that I read a couple of years ago, and this was during a period where I thought it would be interesting to track down the origins of all of these laws that we know about. Moore's law, Conway's law, there's a long list. And part of the reason I wanted to do this was a belief that my understanding of what these laws are meant to convey might actually be quite different from what the original author's intent was. And that turned out to be, I think, the case in terms of Conway's law. So Conway's law, is written up here. So organizations which design systems are constrained to produce systems which are copies of the communication structures of these organizations. So Conway's basically postulating that in a large design organization where you have many different teams that are collaborating to try to build a giant system, it's natural for there then to be created basically an isomorphic relationship between the components of the system and the components of the organization. And I first heard this law, I think, when I was in college, and it seemed like a pretty depressing observation to me. I thought, this is just saying that design basically is heavily influenced by the broken organization of large companies. At least that's how I interpreted it at the time. When I went back to read the original paper, though, I found out that it wasn't meant as a cynical observation. Rather, it was meant as an observation, as a statement of facts. And then based on this fact, how can we actually improve the situation? So the title of the paper is kind of funny. How do committees invent? And these days, design by committee, of course, is sort of a pejorative, right? We typically don't think that committees are capable of designing something. They lack, sort of like an ethereal voice, if you will. But in this paper, Conway begins by sort of talking about how the software industry is changing. And in fact, he mentions that the software industry is this new thing. He describes how, for the first time, we're seeing computer companies, in other words, hardware companies. There are actually companies coming out of them which specialize just in software, and that's a big difference. And the sorts of systems that he talks about designing, like missile defense and other things, very much products of their time. So I think one reason I would recommend reading this paper is just because it gives a very interesting, historical perspective on what the computer industry was like in the late 1960s. But back to Conway's law itself. So, we have this observation, right? And the rest of the paper really is about what can we do based on this fact. So Conway, draws a couple of corollaries. So one is that in light of this fact, a design effort should be organized according to the need for communication. So, Conway sees this issue where if you have 100 people who are collaborating on the design of a complex system, you can't have each person talk with the other 99 people because very quickly you'll just bog down in communication. And we see actually the same thing in distributed systems, right? It's important to route information in an efficient manner in order to prevent saturating your network fabric, and for that matter also bogging down your nodes with just needless communication traffic. So the second corollary is that because the design which occurs first is almost never the best possible, the prevailing system concept may need to change. Therefore, flexibility of organization is important to effective design. So Conway's saying that at the beginning of the design process, we don't know what the eventual system is going to look like, and that we just need to accept the fact that any organization that we start with will need to change over time. So you may also interpret this as kind of depressing because it's almost like he's postulating that a healthy organization is one that's constantly reorganizing itself. And certainly corporate reorganizations get a pretty bad rap for many legitimate reasons. But I think in this case, he's really advocating more that the things that people work on be somewhat more fluid than they are, and that ownership be spread across the organization. So at the end of the paper, Conway makes an important prediction, and that's really sort of the theme of this talk. So his prediction is that it becomes necessary to restrict communication so that people can get work done. And research which leads to techniques permitting more efficient communication among designers will play an extremely important role in the technology of system management. So I want you to stop for a second and think about some of the tools that software engineers use today that were not available in the late 1960s. Things that we really take for granted, things like version control, things like code review, be it Review Board or Fabricator or GitHub, and other tools like that, and that Jira, for example, also, or bug tracking systems. And when you get down to it, like each of these tools is really a mechanism for communication. So version control in many ways is a mechanism for communicating with the past. You're able to see the history of how something evolved. You're able to look at commit messages and understand why a change was made. And with Jira, you're also able to understand how different pieces of the project connect together. Timelines, you're able to ask questions of other developers, leave comments. And all of these things, right, are able to streamline communication. Like in particular, things like Git using git blame, or Jira using search functionality, you're able to quickly find basically the person that you need to talk to. And that's huge. Without these tools, right, in a 1960s era organization, you would really have to talk to a bunch of people maybe before you would be able to find the engineer who's working on that specific piece of code that you're looking for. So I want everyone to just sort of think about how, in my opinion, Conway's predictions really are quite accurate. And I think it's important to appreciate that. So let's take it as a fact that a lot of tools have improved the communication between engineers for the task of developing software, and that this has allowed us to build ever larger systems and to get around the problem that Conway formulated in Conway's law. The unfortunate thing is, though, that these same practices have lagged in terms of being adopted for data engineering. And in data engineering, we see many of the same problems. At LinkedIn, we see a problem over and over again where the people who are producing data sets, the people who work on online teams, they are generating events based on user interactions with the system. And for them, in many ways, it's like they're putting a message in the bottle and throwing it in the sea. They have no idea who's going to pick it up. They have no idea what is built on top of it, the offline data processes that depend on different aspects of that message. And when they make changes, it often has very disruptive effects on people on the other side of the company. So, this picture then really is meant to illustrate the fact that there's this haze, right, a mist that exists between producers and consumers. And there's no easy way for a data consumer to communicate with the person who's producing a data set they depend on. And similarly, the reverse is true. Producers really have no idea who's depending on their data sets. And even if they did, I'd argue that it is still very disruptive for a data producer to make a change, in particular to a schema. There are many types of changes, in fact, that are prohibitively expensive to make, such as removing a field, right? Until you can get everyone migrated off of that field and over to a new field, it's really impossible to do. And as a result, at LinkedIn, we have many tracking data sets that have lots of vestigial tails, columns and fields, which everyone knows they shouldn't use. There was one incident where we had 2 columns in a data set that represented time, one in milliseconds and one in seconds. Someone got confused about which column was the right one to use, and it caused metrics to go, haywire for a week. So that was a very, simple problem, but it simple cause of a big problem. And it's that sort of thing that we would really like to try to avoid. So going back to software, let's take a look at how change of interfaces, in particular, the change of contracts between the implementer of functionality and the consumers of functionality is handled. So another sort of interesting thing to note is that Conway's law and Conway's paper are frequently brought up by people who are talking about microservices, because they say, microservices are a great example of how we get around Conway's law by breaking everything down into small pieces, and that makes things much more dynamic and easy to change. So in a service, of course, a microservice, it's easy to introduce a new API because you can support both the old API and the new API on top of the same service at the same time. Unlike data sets, right? In a data set, unless you're willing to maintain two different copies of the data set, you have this point where you at some point need to flip over and begin publishing the new version. And that's like an atomic force push upgrade, right? If people aren't ready for that upgrade, it's going to break everyone at the same time. And that's really why these backward compatible changes in practice just don't happen, because people know that the cost is way too high. But like I said, for services, there is a way of making these changes, even backward compatible changes. You simply introduce the new version of the API. You watch as people migrate during a window of time from the old API to the new API, and then you gradually turn off the old API. So we would really like to have this same functionality, this same ability for data sets. And that's what Dali provides in the form of views. So many of you probably are familiar with SQL views. A view is basically a query that looks like a table. So when you query the view, if it's a virtual view, the database goes and basically rewrites the view query on top of your query and executes the whole thing. If it's a materialized view, you can basically tell the database that you want it to materialize that view. The database goes and runs the query and then saves the results. So in Dali, the views are virtual. And that means that, in effect, the people who own data sets are able, using the view, to manage or to decouple the implementation of their data set, which is basically the data on disk in distributed storage, from the interface of the data that they expose to clients. So they are able to also support multiple interfaces, APIs, on top of that data set at the same time. And this gives data set owners and data producers the same power and flexibility to manage the API of their data set that people who build microservices today have. So how did we do this? We basically did it by originally embedding a database engine inside of the reader layer of Spark and Hive and Pig and Presto. More recently, we've actually started doing this through code translation. So we're able to translate from different flavors of SQL into an intermediate relational representation, and then from there to the target language using Calcite. We've also introduced a tool or a framework called Transport, which allows users to write transportable UDFs, which covers the other sort of half of this equation. So sort of digging down a little bit more into the abstraction that Dali Views provides. A table, of course, is an abstraction that wraps over physical information like the path on distributed storage of a data set, the format, schema, partitioning team indexes. The view really is a function expressed in SQL, described in terms of other tables and views. And a Dali view in this case is a view plus a table plus UDF dependencies. So we give you the ability to manage a view like you would any other software artifact. You check it into Git, you declare dependencies that the view has on UDF artifacts, basically jar files, and specific versions, and you're able to version the view as well. So sort of in recap, what are views good for? So at a high level, they're good for giving data producers the ability to manage the contract that they expose to data consumers. But if we dig down a level, they're also good for a variety of other sort of like concrete use cases. Going through the list, so one is flattening highly nested data without storing two copies. At LinkedIn, there is a profile data set for member information, it has 8 levels of nesting. And in SQL and Pig, it's really inconvenient to deal with that, many levels of nesting. So it's convenient to store a flattened copy of that. We're able to do this, basically offer a nested and a flattened version without actually making 2 copies. And that ensures also that the flattened version never falls out of sync with the nested version. Another useful thing is to be able to demultiplex a generic table into 2 specific tables. So this is a case where, in effect, we've unioned 2 different event types together. And rather than having people in their business logic always filter on the event that they're looking for, it's a lot easier if that filtering is already sort of encoded in a view. And the reverse is also true. So we've seen cases where people create these synthetic union views on top of a bunch of different specific page view types. I also mentioned managing backward incompatible changes without materializing 2 copies. So it gives consumers the ability to remove fields without disrupting downstream users. We've also used it to bridge the gap over different storage formats. And code reuse is a major thing also that I wanted to talk about. So in the past, there were many cases where we might see something that people were doing in a bunch of different queries or Spark jobs. They were basically writing the same logic. And the solution at the time was to say, well, let's write a UDF, and everyone should use this UDF instead of writing their own code. The problem, though, then became actually versioning and managing that UDF and making sure that everyone was using the same copy. We would often see cases where people were using old copies of the UDF, or another issue was that we'd have to write different UDFs for the different compute platforms that we were using. By pushing that logic that everyone needs into a view, we're able to make it accessible and reusable by everyone. We're also able to hide the complexity of the implementation, and we're able to version it and make sure that everyone is on the same version at the same time. So code reuse, just like we see in software, is a huge use case and motivation for views. And really, the larger theme here is taking all of the nice tools that we have for software engineering and applying them really to the problem of data engineering. Eventually, what we want to do with this is really take advantage of the notion of, instead of thinking about a graph of workflows, we'd like to think more about a graph of views. And if we have the ability to introspect into what those views are, it opens the possibility of really modeling your graph of views as one giant common table expression, and asking your SQL query optimizer to go and figure out the different opportunities for scan sharing, predicate pushdown, and things like that. So just to summarize quickly, why Dali gives our users the ability to move seamlessly between physical and virtual data sets. That has had a huge impact on productivity. Code reuse is another major issue. So we've been able to eliminate a lot of boilerplate logic that users were managing in thousands of different pieces of business logic. And dependency management has been huge. So it allows data producers to understand which downstream pieces of logic depend on the schema of their data set, and to do impact analysis. And also, in the rare cases where something does break, it allows data consumers to easily trace back upstream and figure out what changed most recently, and then use that to narrow down the cause of their problem. So Dali is also format and storage agnostic, which these days I think people are increasingly taking for granted, which is a really good thing. But in 2009, when I joined, actually I joined LinkedIn in 2012. In 2012, when I joined LinkedIn, things were still not storage and format agnostic, and this was a big problem. And then finally, it decouples data producers from data consumers, and this is really I think the main point of Conway's law, right? Like, given the fact that people are connected, how can we decouple changes as much as possible, and in cases where they are coupled, streamline the communication between individuals who need to know about each other. So that's the end of my talk. There's actually a longer version of this talk that you can find on YouTube if you're curious for more information. And anyone who wants to follow up with me, I'd be happy to answer questions either over LinkedIn or on Twitter. Thank you very much.